Hello students, welcome back. So far we were discussing orbital angular momentum, and we have seen that L square and Lz has simultaneous eigenstates written by Lm. So we have L square operates on Lm, you get L plus 1 h cut square, and we have seen Lz also have a same eigenstate, so eigenbasis, and the value is Lm. Similarly here, Lm. Now, we're going to discuss about the spin angular momentum. The theory we have derived for the orbital angular momentum is also applicable to spin angular momentum also. So for spin angular momentum also, we can define a operator S square operates on a state S, and now I'm writing it as SMS, and you get the eigenvalue S plus h cut square as ms. Similarly, when sz operates on this one, you get the eigenvalue ms as ms. The only difference between these eigenbases and eigenbasis of s square is that eigenbasis of L orbital angular momentum can be represented by functional form. We have seen that these eigenstates are nothing but the spherical harmonics when we represent when we do their representation in coordinate form. So, but here these states are abstract. They do not have any functional representations because spin angular momentum in quantum mechanics is a intrinsic property, like you have a charge and mass. Similarly, particles have intrinsic angular momentum, and this spin angular momentum had nothing to do with the space motion. So they don't have any space like r theta variation wave function. So now we have seen this s square sz. Now let me write for s plus also. What is s plus? So when s plus operates same like L plus, this will give you under root s plus 1 minus m plus minus 1. If you write plus minus here, and then you have h cut. So now I'm going to use this expression. Now let us discuss first spin half particle. Spin half particles. So like your fermions, okay? Fermions can have a half integral spin. Boson can have an integral spin. Like photon has a spin 1, and if I talk about electron has a spin half. So spin of electron can be there are two states. So I can write SMS. So SMS for spin half particle, there are two states. One is a spin half half, and other is a state half minus half. For given S, there is, if the S value is half, MS value can vary from minus S plus 1, 0, and up to S. So when S is half, MS value can be either plus half or minus half. That means you have only two states for spin half particle, spin up and spin down. So I call this spin half minus half as a spin up state, spin up states. Similarly, this is half minus half is called spin down state, spin down state. Now, these states are form orthonormal basis. That means any function can be represented as a linear combination of these two states in two-dimensional Hilbert space, because these two states form a two-dimensional Hilbert space. And now this state also represented by, because this is a spin up state, so generally we write, because this is the eigenstate of Z, so we represent this state by arrow, up arrow with Z component. And similarly this state also represent in this way. I usually represent this state by Z plus, and I represent this by Z minus. So this is the eigenstates of SZ, Z direction, spin state in Z direction. So we are writing Z. If the states are in the X direction, we write X or Y. Now we see, I want to find, I want to operate my S plus, because I want to find Sx. Okay, so for Sx and calculation of Sx, Sy, and Sz, Sx and Sy, we need ladder operator. Sz we can directly write from here. If I want the matrix representation of Sx, so Sz is what? Sz, there are two states. So I can write, say, Z plus Sz, Z plus, and similarly, I'm writing Z plus Z minus, so Z plus Sz, Z minus, and similarly you can Z minus Sz, Z plus, and you can write Z minus Sz and Z minus. And we know how to, here Z is half. So when Sz operates on Z plus, what you get? You get h cut by 2, because S value is half, and Z plus, and when you Sz operates on Z minus, you get minus h cut by 2 Z minus. Now let me write here matrix form here. So when Sz operates on Z, you get state doesn't change. You get h cut by 2. So I can write here h cut by 2. This state will become 0. This element will become 0, and this element will become minus h cut by 2. Minus h cut by 2. So my Sz matrix becomes now h cut by 2, 1 0 0 minus 1. Similarly, I want to find now Sx and Sy. So this state also is represented by 1 0 and 0 1. So these are the eigenstates of Sx operator. Now let us write a representation of Sx and Sy in matrix form. So for that, I need to operate, say, S plus on plus Z state. That means I want to operate S plus on half. So when I operate here, because you cannot increase now M, so this should come 0. So if I write eigenvalue S plus 1 minus half plus 1 h cut, this comes out 0. So when S plus operates on plus state, it gives you 0. And when S plus operates on minus Z state, that means S plus when operates half minus half. So what will become if he operates here? This becomes 0. Here you have, this doesn't change. So this is 3 by 4 minus, now it is a minus half. Okay, so this minus become plus half, and then you have here again minus half. So minus half plus minus. Okay, you have minus here. Here plus is there, so so minus half plus 1. Okay, minus half plus 1. So this gives me h cut, and state becomes now these states become now half, half. So now that means operation of S plus on minus Z states gives me the eigenvalue H cut, and now Z minus Z becomes plus Z state, because state changes by m plus 1. So this is the operation, and similarly I can show when S minus operates on plus Z, you get again the eigenvalue H cut, and Z changes to the minus Z. And when S operates on minus Z, now minus Z means minus half, you cannot further decrease by operation of ladder operator, so this term becomes 0. So I have now the equations for S plus and S minus. So I can easily write now the Sx, because S plus is what? S plus is Sx plus iota Sy, and S minus is Sx minus iota Sy. So my Sx will become, you have to add this thing, 1 by 2 S plus S minus. Okay. And similarly, Sy becomes, if I want to find Sy, I have to subtract these things. So this becomes 1 by 2 iota S plus minus S minus. So let me first write the matrix form of S plus. Okay. So how can we write a S plus matrix representation? So S matrix representation of S plus, let me go next page. So we have S plus matrix representation. I go plus Z, S plus Z, plus Z, S plus minus Z, plus Z, minus Z, sorry, minus Z, S plus Z, and you have a minus Z, S plus minus Z. Now these are the matrix element, and I told you when S plus operate on Z plus, it cannot enhance, so this becomes 0. And when it operates on minus this one, so this become plus, and you get the eigenvalue H cut. So this will be H cut. Similarly, this becomes 0, and this become H cut, but here it will change, so this will become also 0. So this is S plus. Similarly, I can write for S minus. So here I write S minus. Okay, S minus operates on Z. It changes to minus Z, so this term becomes 0. Okay, this term will be also 0. Here H cut minus Z, so this term here H cut will come, and here you have again 0. So I have S plus and S minus. Now I can write Sx. Sx will be what? Sum of these two. Sum of these two means 0 H cut, 0 Sx definition is 1 by 2 S plus S minus. So 0 H cut 0. So this become Sx become H cut by 2 0 1 1 0. Okay. So this is your representation of Sx. We have already seen the representation of Sz. Sz was 1 minus 1 0 0. Okay. So we have S Z H cut by 2 1 0 0 minus 1. So we have Sx Sz, and now let me find the Sy. Sy will be 1 upon 2 iota S plus minus, this is minus, so 0 H cut minus 0 H cut, 0 minus H cut, and this is 0 0. So if I take H cut common, H cut by 2 common, this iota I can write as a minus iota. Minus iota means this becomes 0 minus iota 0. So this is representation of SYA. So now I have all the three Sx, Sy, and Sz. I have Sx, Sy, and Sz. So Sx I can write as h cut by 2 sigma x. Sy I can write it as h cut by 2 sigma y. Sz I can write it to h cut sigma z. Now sigma x is what? Sigma x is your 0, 1, 1, 0. Sigma y is your 0 minus iota, iota 0. And sigma z is your 1, 0, 0, minus 1. These are called poly spin matrices. Is called poly spin matrices. And now you can find the eigenstates. Eigenstates also, like we have seen for Sz, the eigenstates were 1, 0 and 0, 1. Similarly, we can write now eigenstates for other operators also. So now I'm writing directly the eigenstates. So I wrote Z plus is, I told this is 1, 0. I told Z minus is your 0, 1. And now we can find out and we can prove that y plus, okay, y plus is 1 by root 2, 1 iota, and y minus is your 1 by root 2, 1 minus iota, and then you have z we already written, now x. So x plus is your 1 by 2, 1, 1, 1, 1, 1, and x minus is 1 by root 2, 1 minus 1. So these are the eigenstate. So these form orthonormal basis. Similarly, these also form orthonormal basis. Similarly, these form also orthonormal basis. So any function can be represented by linear combination of these the eigenstates of z plus, y plus, and sx, sy, and sz eigenstates. Okay, so I'll stop here. In next class, I will discuss the properties of these poly matrices, and we'll drive a little bit more deep inside these states. We'll see what is poly matrices. I'll stop here.